content or other things, ask me. I heard that the book is sold out. There is one more copy remaining. And if you email me, I will forward you to the graduate student. From today, we will focus on proving something. So essentially, in this course, you will be asked to prove many, many things. And typical thing that we will use most is this one. We prove something by contradiction. Why? Because in many cases, straightforward proof is almost impossible, very difficult to find. So instead of straightforward way, we contradict the statement. And I will show you some example today, and then later we will cover many examples. So proofs by contradiction is the most one that we will use. And some easy cases using mathematical induction. And today we will focus on induction. Of course, I will show you an example of using a proof by contradiction, and induction will be used later. So let's look at one example. But before going any further, before proving something, we need some background. So we prove from this point. We prove this from this point. But before this, something exists. So it is called set theory. And before this, it is logic. And these things is built on top of something called axioms. So roughly, we don't want to touch these things in this course. But if you take courses such as set theory or logic, then you will consider some material that is more basic than this proof thing. So we focus more on afterwards, not before set theory. So what kind of things are covered in set theory? One thing that is covered in set theory is well-ordering principle. Because you can find this from the textbook. You can, I don't want to write down the full statement of this theorem or principle, because you can easily find. I will focus on the idea part more. The idea is this. Assume that we have integers which is non-negative. So integer which is non-negative, set of integers which is non-negative, then for any subset, any non-empty subset, so we don't want to consider trivial sets, so any non-empty subset has a smallest element in the set. So you can find the full statement in the book, but I want to focus more on the ideas. So any non-empty. So it's very trivial fact. As you can see, we pick some subsets such as 5, 10, 11, 12, and so on. Then in this set, can you find the smallest number? Of course, assuming these numbers are bigger, then this is the smallest number. So in any subset, we can find the smallest element. So this is called the well-ordering principle that we don't want to prove, and we don't want to focus too much on logic or set theory part. We want to build on top of these assumptions. But if you are interested in more basic thing than just proof part here, you can study set theory or logic or more things. But in any case, we will use this well-ordering principle today. And in fact, this is used in today's proof and division algorithm proof. In other words, to prove division algorithm, you need to know this principle. Very simple principle, but you need to know. So we create some non-empty set. Then automatically, this non-empty set should have the least element, right? The least, smallest element. So in short, I will use these things. Well-ordering principle. So well-ordering principle. Then, what kind of thing can we prove using well-ordering principle? So, I will write down the statement. Assume that we have two positive integers, A and B. Then the statement is this. We can find some large n satisfying this. N times A is greater than or equal to B. Or just greater than B is okay too. So we can attach equality or you can detach it, doesn't matter. So do you get it? Pick two numbers, 5 and 1 million. Then 5 times 1 million is greater than 1 million, right? So that's there, right? So we have this statement. So knowing theorem is not very difficult in number theory, but proving is the key. It's not just knowing. Of course, we know this fact, but prove it. So now you see two important facts. One is proof by contradiction, and then well-ordering principle. So always we need ideas, right? So the idea is using a proof by a contradiction, right? By a contradiction, and we apply the well-ordering principle. So by the combination of these two, we can prove. So don't be misled. We handle numbers, but we are not interested in addition or subtraction of numbers. We are interested in proofs. So I will prove it. So the idea is this. I want to use well-ordering principle, and well-ordering principle requires a set. Do you follow me? Requires a set. So I want to make a set, which is non-negative. So how can we create a set? That is the key idea. In well-ordering principle, the set includes non-negative integers, right? Non-negative integers. So I want to make non-negative integers. So why do we need contradiction? So I will show you the idea of this contradiction. So this is the idea. Assume that this result is false. This is the typical technique. All the time you should follow this pattern. Assume that the statement here is false. False for all n. So you are seeing the technique. When you want to prove something, we use contradiction, proof by a contradiction, how we somehow assume that this is wrong, the result is wrong. So this is the key idea. Then, because of this fact, using something, we lead to a contradiction. So I'm not proving it now. I'm just explaining the method or idea. We assume that the result is false. Why? Because of something. And then after showing that this lead to a contradiction, we say that this should be true. Because if we say this is false, we encounter a contradiction. Do you follow me or not? So we say this is false, and then we lead to a contradiction, and then we come back and then say, why a contradiction happened? Because of this. So it should be true. So I explained the idea. Then, where does this work? When we form something, we use a set. Then this kind of set, use this. So combination of this. So this is a two-step proof. So it's tough. One-step proof, normal people can do. Two-step, a little bit brilliant people can handle. So let's do it. So assume that this is false for all n. In other words, if we negate this one, then it means this. B minus NA is greater than or equal to 0 for all n. Do you follow me or not? So I will be slow, and you must follow my statement. Why? Because this is false for all n. In other words, for all n, the other side is bigger, right? The other side is bigger. In other words, the other side minus NA is always non-negative. Under this assumption is false, right? This is false. Under this assumption, we lead to this conclusion. Then now, we have plenty of numbers like these, right? Such as B minus 0A, B minus A, B plus A, and also this n could be negative, then B minus negative 1A, B minus negative 2A. And we have plenty of things like these, but in short, we can just use simple notation, B minus NA, where n is an integer. And it is very trivial to show that this is non-empty, because assume that n is 0 or n is 1, then A plus B is already an integer, right? Non-negative integer. In any case, we created a set. We created a set. Do you follow me or not? Under this assumption that the result is false. Then now, we say that by well-ordering principle, the set, let's name this set. Let's name this set S, right? By well-ordering principle, the set S has the smallest element, right? The least element say any letter. So let's say capital N, right? In other words, this is a set. Then by the well-ordering principle, the set should have the least element. So we call that least element capital N. Do you follow me? It might be misleading because of N and N. So I will change the letter to something else. So I will change this M, right? Because you may think there is a relation between that and this N. So there is no relation, just M. If you don't follow me, ask me. So it's very, very tough because each line depends on previous line mostly. So if you miss one thing, the following thing crumble, right? The following things crumble. So under this situation, what conclusion can you get? We can get this conclusion. The set, I will recap what we arrive at, recap, and we have this conclusion. The set like this. B minus NA, this set has the least element, the smallest element. What is the least element? M. Right? This is the conclusion. Then the next thing is this one. We consider this kind of number. Consider, so this is just restating this thing. Now consider this number, m that we found minus a. Then m minus a equals b minus na minus a, and then b minus n plus 1a. So I will pause and please check these steps. We found some number that is the smallest element in the set. Now we consider some number called capital M minus A. Then capital M minus A equals, by this definition, B minus this one, and then this one is trivial calculation. And then this has a pattern, B minus some number A pattern, right? This is the B minus A pattern. So this number is also, every form pattern has in the set S. So we replace this by integer n plus n, because n is an integer, n plus 1 is an integer, right? Then what happened? The number here is smaller than the number, but it's a contradiction. Because I said m is the smallest number in the set. But m minus a is clearly smaller than m, right? M minus a is smaller than m. In other words, we have a contradiction. Thus, the result cannot be false. Thus, this should be true. Right? This should be true. So I completely showed you how to prove it. So you should have this proof structure in your head. In other words, in the future, if you encounter some problem like this, then you should know what kind of things you need to do. So it's way different from any calculus course or any calculation course. Differential equation, all those things just require routine technique to arrive at the result. In this case, absolutely not. So as I mentioned before, someone who took many courses in science and engineering told me that this was the hardest course because of proofs. In any case, I completely showed you the 4 steps required. Then what is the key thing that I see? The key thing that I see is this one. Assume that you cannot follow everything and cannot remember everything. And what I want to see is this one. I want to see this statement. In other words, you should say that the result is false, right? If you want to use a proof, use proofs by contradiction, then you should say the result is false. And then do something, and then you arrive at a contradiction. So I want to see two things, and something in between, filling the gaps, right? So you should say the result is false. In what pattern? you say, assume that the result is false, right? Assume that the result is false. Then you arrive at a contradiction. Thus, we cannot say the result is false. In other words, you proved it. So this is a harder part of proofs. But today, instead of focusing on harder part, we will use easier thing called mathematical induction. And then later, we will use these things over and over again. But today, it's just an introduction. But please browse the note and follow these things and ask questions. If you have any doubts or difficulties, ask. Then the next thing is induction. And induction is, in some sense, easiest way to prove something. So there are many versions of induction. So we will use this coarse version. So this coarse version of induction, right? So this coarse version of induction is this one. We prove by two steps. Prove that the statement is satisfied just one integer. One integer. One integer. It could be, for instance, 0. It could be 1. It could be 2. It could be 5. It could be 10. So the statement is satisfied by one integer. And second thing that you need to prove is this one. If the statement is true, right? If statement is true, I will write a little bit detailed description. If it is true for k, then it should be true. It is true for the next number, k plus 1. So if you show these two steps, then you can say, by mathematical induction, you proved it. So there are two steps required. So in this sense, it is way easier than a proof by a contradiction. If you use a proof by a contradiction, you should find your own way. But in this case, it's very routine. It's very routine. You show that the statement is for one integer. And then you prove that if the statement is true for k, then it is true for k plus 1. So it's way easier. So I will show you an example. But if you have a question, ask me. Why did I attach this thing, this coarse version? Because some books are very strict. Some books do not allow any number, just 0 or just 1. Some books only require 0 or 1. But I don't want to require anything, just one integer. So if we use 0 here, then we can just say mathematical induction. But there is no big difference between one integer, such as 10 or 11, or 0 in this proof. So I attached this coarse version induction. It's not very different from actual induction. But to make things convenient, I attached it. No questions? Then let's continue. Excuse me. So prove that 1 plus 2 plus 3 plus everything up to n equals n plus 1 over 2. So question is proving it. Question is not about knowing this fact. This fact is studied in maybe middle school or high school, but proving is the requirement. Then, to make this thing a little bit more rigorous, I will use a lot of dots. So first part is showing this for any number. So if n equals 1, then the left side is 1. The right side is 1 plus 1 over 2 and 1. And they are equal. Done. So I proved the first part. Then it's time to prove the second part. Assume that it is true. Assume that it is true for K. Assume that this statement is true and n is K. Do you follow me? Assume that it is true, the statement is true for n equals K, then 1 plus 2 plus 3 plus K equals K plus 1 over 2. Because I assumed, right? Because I assumed that it is true for n equals K. So I showed. Then the next step is adding K plus 1 to both sides. If I add K plus 1 to both sides, then I get this relation. Do you follow me? I added K plus 1 to both sides. Then I can rewrite the right side by factoring out the common factor. The common factor is K plus 1, so I factored out K plus 1, then K over 2, and 1 remain. Any questions? Then I can use the common denominator 2. So what I did was this one. This K plus 1 came here. This portion came here with 2. Then take a look. If we assume that this is true for n equals K, then take a look. If we replace n by K plus 1, then we get this result. So we proved it. So I proved the step by showing this. So second step is done. So by 1 and 2, or we usually say by induction, by mathematical induction, and 1 and 2, right? By mathematical induction and 1 and 2, we are done, right? So this is very typical. So when you want to use induction, you should say it holds, the statement is true for one number. And then the second one is the harder part. Assume that it is true for K, then it is true for K plus 1. Some books has different flavor. Some books say, assume that it is true for n minus 1, then it is true for n. So there are some different flavor, but essentially the same idea. Then instead of worrying about the details, let's consider the situation. Because of the second part, what happens? If it is true for K, then it is true for K plus 1. In other words, assume that it is true for 5, then it is true for 6. But because of the same statement, if it is true for 6, then it is true for 8. Do you follow me? In other words, this second statement traverses all the numbers afterwards, right? So initial number is chosen by first statement, and the second step traverses all the numbers. In other words, because of the second fact, the next number is true, and the next number becomes the input, and new output is the next number, and the next number becomes new input, and the next number. So it is like an engine, right? It rotates and rotates and then proves all the way. So this is the idea of mathematical induction. Any questions? Then there are a few examples that I want to show you, and then go to the next case using binomial theorem. And one more example that I want to show you is this thing. One is prove that 1 squared plus 2 squared plus 3 squared up to n squared equals n 2n plus 1 n plus 1 over 6. Then what should we do? First of all, if n equals 1, then the left side is 1 squared, and the right hand side is 1, 2 times 1 plus 1, 1 plus 1 over 6. And as you can see, 1 times 3 times 2, 6 over 6, 1. So left side is equal to right side, right? We are done. Now second part. If it is true for k plus 1, k, then the left side is 1 squared plus 2 squared up to k squared equals k, 2k plus 1, and then k plus 1 over 6. Then the next thing is showing this for k plus 1. So to do it, I should attach one more number. This is given. Then attach one more number, k plus 1 squared, right? I attach one more number. Then I attach one more number on both sides. Then, from this point on, is calculation after calculation. So I will do it. First of all, I will factor out the common factor, k plus 1, and k plus 1 here. Do you follow me? I will factor out the k plus 1 and k plus 1 factor. So k plus 1 is the common factor. And then this portion has, I multiply this out, 2k squared plus k. Do you follow me? This portion is remaining after factoring out k plus 1. And then if we multiply this out, then we have 2k squared plus k. And here, because we extracted k plus 1, we will have k plus 1. Then k plus 1 is here. And then 6 is the common denominator. 2k squared plus k plus 6k plus 6. Any questions? Then the numerator is 2k squared plus 7k plus 6. And can you factor this out? So I factored out the numerator term appearing here. Of course, this course is not college algebra, so I don't want to show you the details why this is so. It's covered in college algebra. So I will write down the factor the result. K plus 1, and then 2k plus 3, and then k plus 2 over 6, right? 6. Yes?
Can you go back to the top of the page?
Excuse me?
Can you go back to the top of the page?
About here? Or way high?
Oh, no. Yeah.
So please check whether you follow everything up to this point or not. Then I will rewrite it. Then take a look. If you replace n by k plus 1, you exactly get this result. In other words, second part is done. So, by induction, done, right? By mathematical induction, we completed the proof. So in this sense, this induction method is very straightforward method. Or you already know what you need to do, right? You should prove the statement for one number, and then this statement, right? If it is true for k, then it is true for k plus 1. Then we prove the engine part, right? This engine runs and runs and runs, and then traverses all the way up. Any questions? So there are many cases using this idea, but I do not have enough time to cover everything. So I will cover one more interesting case and then go to the next section covering the binomial theorem. The next thing is this one. I will rewrite it. So this is the statement, right? 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, and so on up to 2 to the power of n minus 1. And then add all of these numbers. Then it is equal to 2 to the power of n minus 1. So prove this. So always this is routine proof, and this is routine. For n equals 1, then it is 2 to the power of 0. So left-hand side is 2 to the power of 0. Right side is 2 to the power of 1 minus 1. Then 2 to the power of 0 is 2 to the power of 0 is 1. 2 to the power of 2 is 2. 2 to the power of 1 is 1. So 2 minus 1, 1. So they are equal. So always this part is straightforward calculation. Any questions? Then second part. Assume that it is true for k. In other words, 2 to the power of 0 up to 2 to the power of n minus 1 equals 2 to the power of n minus 1 with n replaced by k. So I will use k. So we assume the statement for k. Then we can add both sides by 2 to the power of k. I mean 2 to the power of k, and then do you follow me? So I added both sides by 2 to the power of k. Then what happens to the left side? Left side is adding everything from 0's power up to 2 to the power of k's power. And the right-hand side is adding these things. So then 2 times 2 to the power of k minus 1. Then how many times did we multiply 2 here? K times here and 1 more time. So total how many times? K plus 1 times we multiplied. So this means we proved the statement for n equal to k plus 1. So after writing this, you can say by induction, we are done, right? So as you can see, proof by induction is the easiest among all possible method of proofs, right? It's the easiest. Because straightforward calculation. So do you need more examples, or these are enough? If you want more examples, then I can prove it. Even you can ask for any exercise problems or example problems. No questions? Then I will cover the next section, 1.2, the binomial theorem. First of all, I introduced notation last time, and I introduced one more time. We will use n choose k, and then this means n factorial, and then n minus k factorial, and then k factorial multiplied together. So this is the notation. And choose k. And of course, I already let you know the meaning. For instance, if you have m factorial, it means we are multiplying numbers m through 1, right? Or 1 through m. This is called m factorial. And by definition, 0 factorial is 1. These are all definitions. Any questions about the choose notation? Then the next thing that I want to show you, or we will use from now on, is binomial theorem. Binomial theorem is this: a plus b to the power of n equals n choose 0, a to the power of n, b to the power of 0. So you should see matching numbers. And then n choose 1, a to the power of n minus 1, and then b to the power of 1. So I will attach intentional negative 0 here to match numbers, right? And then now we will have 1, 1, 1 here. And then generally, for some k, a to the power of n minus k, b to the power of k, and then all the numbers up to this point, and then n choose n, and then a to the power of n minus n, then b to the power of n. So I match these numbers. So this is the binomial theorem. So we will use this theorem in this course, and I will show you that this is true for general cases, but this proof is very long, so I will omit the proof of this statement. Because this is very long calculation, and we don't have enough time to cover everything, but the idea is not very difficult. First of all, we want to prove this statement for any n. So what should be the first line, first step that you should do? You should prove this for what? 1, right? So you should prove this for 1. And then the next step is you should prove this assuming that it is true for k, and then you should prove this for k plus 1, meaning you should multiply both sides by a plus 1. But if we multiply a plus 1 everywhere, it is very large, right? So I don't want to show you the full proof, but if you want the full proof, there are two ways. You may read the book. If you don't understand the book, you come to my office, then I will show you, or you can meet the SI, right? In any case, this is the statement, and we can prove even this statement using mathematical induction. So you can show that this is true for n equal to 1, and then or n equal to 0. And then you can prove this, assuming that it's true for k, and then k plus 1, it is also true. Then you get. But we will apply. We will omit the proof, but we will apply this idea to prove other things. Right? We apply this binomial theorem in this course. So, what can you say? But before going further, I will show you one more fact. One more fact is this one. N choose k plus n choose k minus 1 equals n plus 1 over k. So I will use this fact, and I can prove it by calculation. So let's use previous facts to prove this. So I will prove this thing on the right side, and take a look. What is n choose k? N choose k is what? N factorial over n minus k factorial, and then k factorial. And what is n choose k minus 1? The same n factorial, and then n minus k minus 1 factorial, and then k minus 1 factorial. Do you follow me? So we want to mix these two things by extracting the common factor or common denominator. So we want to extract maximal common factors. So from the numerator, what is the maximal common factor that we can extract? Thank you, and factorial. From the denominator, what is the maximal factor, maximal term that we can extract? I will rewrite this thing to show you. So the maximal term that we can extract is n minus k factorial, because one number is bigger, this number or this number. One number is bigger, this number is bigger. That means we can extract a smaller number. Do you follow me? And then here, one number is bigger. K is bigger, so we can extract a smaller number, k minus 1 factorial. So I extracted maximal factors that exist, right, in both terms. But if you don't agree with me, ask me. I extracted the maximal factor from the numerator, from the first pattern, from the second pattern, and then I will write down the remaining terms here if you don't have a question. Do you follow me? M minus k factorial, m minus k plus 1, 1 bigger than the previous number. So the factorial is the product of this number all the way up to 1. In other words, it includes all the way smaller than this one, right? That means it includes the above number. So the same is true for k minus 1 factorial. Then the remaining term here is, because this portion is extracted 1, and then because this portion is extracted 1, and because k minus 1 factorial is extracted k. Do you follow me or not? And the next term, the maximal term we can extract from this is 1. And the maximal term that we can extract is m minus k plus 1, because factorial part is handled here. And then k minus 1 is already extracted. So this is true. Yes?
I don't understand the k plus 1 part, the n minus k plus 1.
Mm-hmm.
I thought it would just be n minus k.
So I will write down n minus k plus 1. N minus k plus 1 factorial equals n minus k plus 1. And then what is one number smaller than this one? M minus k plus 1 minus 1, right? One number smaller than this, and so on. So we have all the way up to 1. So this number is called m minus k factorial. Any other questions? Then let's write down the complex part, right? This is complex part. So I will extract this complex part and then calculate. So 1 over k plus n minus k plus 1. Then we can use the common denominator, k multiplied by m minus k plus 1. Then it is m minus k plus 1, and then k. K and k are cancelled out, so n plus 1, and then k, and then n plus 1 minus k. So please check this calculation. Then we can mix these things to find the result. So this is already there, and then now this is simplified in this form, so I can write down the full result. So I will separate this calculation portion from the major trend. So I will use this portion, but this is not the major portion. I will use this fact to get the result for this part. So I will continue equality downstairs. Then n factorial n minus k factorial, k minus 1 factorial, and then now this one, n plus 1, and then k, and then n plus 1 minus k is written here. Then we can combine these things in one notation. N plus 1, and then all the way up to 1. And through all the way up to 1 multiply. Then can you simplify this thing? What is it? Thank you. N plus 1 factorial. And as you can see, k and k minus 1 factorial are multiplied. Then what should the result? K factorial. And then n plus 1 minus k, and then one less number, that is n minus k multiplied all the way through, then n plus 1 minus k factorial. Do you follow me or not? Then by definition, we can write down this thing. So I proved it. And in fact, this part is necessary for the proof of the binomial theorem. That was the reason why I didn't want to go into binomial theorem proof. It's only one part of the proof of the binomial theorem. So we proved it. Any questions? Then the next part is using binomial theorem. 1 plus 1 to the power of n equals I will write down the binomial theorem and then return back to specific number part later. A plus b to the power of n, and then n choose 0, a to the power of n, b to the power of 0, all the way up to n choose n, a to the power of 0, b to the power of n. This is the binomial theorem. Now, we play the game using specific numbers. Assume that if a and b are equal to 1, assume that a and b are equal to 1, then what happens? It is, the left hand side is 1 plus 1 to the power of n. The right hand side is n choose 0, and then 1, 1, right? So 1, and then all the way up to n choose n, and then 1, 1, right? 1, 1. Because of this, we can get this kind of result. 2 to the power of n equals n choose 0 up to n choose n. So I may ask you to prove this fact. Then what should you do? You should say that by binomial theorem, we have the above fact, and then if we use a equal to 1, b equal to 1, then we can get this result. So proof is done, right? Do you follow me or not? Now, the next nice number set would be what? Can you guess? I picked the nicest number possible, but there is still another pair. What pair do you pick? Do you pick any pair? So this is the general binomial theorem, right? From binomial theorem, I chose this thing. So first example is done. I want to find second example. So can you pick nice pair? If a equals what? 1, and b equals negative 1. So if a equals 1, b equals negative 1. Then the left side is 0, right? And the left side is 0. So 1 plus negative 1 to the power of n is the left side. And the right-hand side is a and 0 to 0. And then 1 to the power of n. And negative 1 to the power of 0. And all the way up to n choose n. And then 1 to the power of 0. And then negative 1 to the power of n. So if we write it, then the left side is 0. The right-hand side is n choose 0 minus n choose 1 plus n choose 2 minus and so on, all the way up to this. N choose n, and then minus 1 to the power of n. So this is the proof. So assume that I ask you to prove this thing, then you should state the binomial theorem, and then specific AB value, AB pair. I will pause, and then you can check. So while I'm pausing, you may browse your note and then check whether you completely follow everything up to this point or not. Then, one challenge question. It's not very difficult, but it can be asked. Instead of showing you the proof, instead of showing the steps, I will state the result, end result. Then you should recover it. So my statement is this one. Prove that n choose 0 plus 2 times n choose 1 plus 2 squared times n choose 2 plus all the way up to 2 choose n choose n equals 3 to the power of n. Prove this. So I will give you 2 minutes. prove this thing. Any questions? Yes?
Either or, the compare the second pair.
Oh, it is, we use the fact that n choose k is equal to n choose k minus 1, then we can flip everything. We can flip these backs, then it can happen. But to stick to the example straightforward, use this thing. Oh, sorry, use the other thing. So use the other thing, and then. In any case, we can prove it. Any questions? A little bit tougher one is something that exists. Do you want the tougher one, or you skip and then go to the next section? It's up to you. There is a tougher one. Do you want to see the tougher one, or go to the next section? Let's vote. Go to the next. How many? Tougher one? Wow. Sometimes, in these cases, they were just one-step proofs, right? But now, assume that it's two-step proofs, then it's tougher. So I will show you. It is something like this. Prove that So as you can see, it is very tougher.
The n-1.
That's right. I will rewrite it in the next line. Any questions? Then, why is it so difficult? Because it's a two-step problem. If it was one-step problem, you might do it, right? Easily. But it's two-step problem, then you cannot clearly see. So you should overcome this kind of difference in the future, but let's see it. So the key idea is given. Key idea is this. N times 1 plus some number b to the power of n minus 1. This is a key idea. And then we write many patterns like these to prove the theorem. So let's do it. If we expand this thing, what do we get? If we expand this thing, what do we get? So n multiplied by this portion, right? This portion. So it is something 1 multiplied by b to the power of n minus 1 here, something n minus 0 here. So I will write I will attach n later so that I can just keep this portion the same as the previous one. Then by binomial theorem, what can you say? I will later attach n, so I will leave some space here. And choose n minus 1 choose 0, 1 to the power of this power n minus 1, and then b to the power of 0. Do you see it? If you want to clarify, you can say minus 0 here, right? It doesn't matter. Minus 0 power. And then the next term is n minus 1, choose 1, and then 1, n minus 1, minus 1, and then b to the power of 1. And all the way up to n minus 1, choose n minus 1, and then 1 to the power of n minus 1 minus n minus 1, and then b to the power of 0. Oh, sorry. n minus 1. So, do you follow me? And then, now I multiply n everywhere, n everywhere. So, if you completely follow me up to this point, I'll attach n everywhere. So let's do it. N, and then n, and then n, everywhere. So I can write down this kind of statement. Then it's time to use specific number, such as b equal to 1. If b equals 1, what happens? b equals 1, what happens? We get, excuse me?
I said lots of garbage will go.
b equals 1, then left side is n, 1 plus 1, right? 2 to the power of n minus 1, right? And then n, and then m minus 1, choose 0, right? And then b equals 1. All these terms become 1, right? All of these terms become 1 when b is equal to 1. So, n minus 1, choose 1, and then all the way up to n minus 1, choose n minus 1. So we get this result. And now, the simplification is required. So as you can see, it's not just one step method. It requires one more step. Do we have enough time? Unfortunately, we don't have enough time. So next time, I will follow this thing. But if you are interested in this problem, you can do it at home and then compare your results. So next time, I will finish this. So let's start.